This is in October, November 2022. We read 42 question, number 9, which carry 3 marks. Figure 9.1 shows the visible part of the emission spectrum from hydrogen gas in the laboratory on the Earth. The numbers indicate the wavelength in nanometer represented by each line. Part 1. Explain how the emission spectrum provides evidence for the existence of discrete energy levels for the electron in the hydrogen atom. This question carries 3 marks. Therefore, you have to say any of the 3 points which is stated in blue here. Number 1, each line in the spectrum corresponds to a photon of electromagnetic wave of specific energy. Therefore, specific wavelength and specific frequency. When the electrons move from a higher energy level E2 to a level energy E1. You must understand that there are 2 important things for the energy levels. The energy levels are given in electron volt and becomes more negative as you move downward from A to E. This means that the energy of the level decreases from A to E. Then the second point is the energy of the photon is equal to the difference in energies, which is E2 minus E1. We take E2 minus E1 because we're going to get a positive value equals to HF. Then discrete frequency must have come from discrete energy gaps. Or you can say that discrete energy changes implies that the energy levels are discrete. Then in part 2, figure 9.2 shows 5 of the energy levels in the hydrogen atom. The wavelength of the radiation shown in figure 9.1 relates to the transition to the minus 3.400 electron volt level in figure 9.2. This is the theory for the question. E2 minus E1 equals to delta E, which is the difference in energy. We take E2 minus E1 to get a positive value, equals to HF equals to HC over lambda. Because F equals to C over lambda, C is the velocity of electromagnetic wave, and lambda is a wavelength. F is a frequency. So from the equation, you can see that the shorter the wavelength of the line, the larger the value of delta E. That means when the delta is larger, your lambda is smaller and your frequency is larger. The electron transition from X to minus 3.4 has the smallest delta E. This is represented by the red line. Hence, the electron transition will produce a photon with the largest wavelength, which is 658 nanometer. Or I can say smallest frequency. Then we have to calculate, we have to show that the energy level of X is minus 1.51 electron volt. This question carries 3 marks. In order to get the 3 marks, you must say that the line 658 is produced by the electron transition from X to minus 3.4 electron volt. So this is the first point. Second point is your E2 minus E1 equals to HC over lambda. H is a Planck constant which has a value of 6.63 times 10 to the minus 34. C is the velocity of electromagnetic wave, and this is the lambda changed to nanometer, 658 times 10 minus 9 nanometer. Now we divide by 1.6 times 10 minus 19 to change it to electron volt. So E2 minus E1 will be equals to 1.89 electron volt. Therefore, delta E is 1.89 electron volt. So your E2 will be equals to 1.89 minus or plus E1. But your E1 equals to minus 3.4 electron volt. Therefore, your E2 will be equals to minus 1.51 electron volt. In part B, the same part of the emission spectrum from hydrogen as in part A, observe in light from stars. In the distant galaxy is shown in figure 9.3. The numbers indicate the wavelength in nanometer. You must understand that 411 nanometer line is produced on Earth by electron transition from A to E. And then the line 435 nanometer is produced by the electron transition from B to E. And then the line corresponding to 48 on Earth is the electron transition from E to C to E. And then the 658 is for the electron transition from D to E. You can see that this is a line from the star, and this is a line spectrum from on Earth. You can see that each line has shifted to a larger wavelength. 658 has moved to 686, and 48 has moved to 5089, and 435 has moved to 454, and 411 line has moved to 429 in the distant star. The lines are the same, so the line just moved the larger wavelength. Part 1. State the name of the phenomenon that gives rise to the change in wavelength. The answer is redshift. Because why? The wavelength for red light is around 700 nanometer. So you can see that the value is shifting towards 700 nanometers, increasing. Then for part 3, state what this phenomenon shows about the motion of the galaxy. This redshift shows that the galaxy is moving away from the observer. Then for part 3, use one of the lines in figure 9.1 and the corresponding lines in 9.3 to determine the speed of the distant galaxy relative to the observer. So this is a formula which you have to use. The delta lambda, which is this one here, represent the change in wavelength. So if you take the 658 line, your delta lambda will be 686 minus 658, which will give it 20 nanometer. And then your lambda is the wavelength of the same line produced by the same element on Earth. That means we take 658, if we take the electron transition from D to E. And then V is the velocity of the galaxy, and then C is the speed of electromagnetic wave. So from here, you can calculate 28 divided by 658 equals to V divided by 3 times 10 power 8, which will give you V equals to 1.3 times 10 power 7 meter per second. You can use any other lines in the diagram 9.3 to get the answer. If I use the line that produces theta, electron transition theta, which is from C to E, that means I would take 509 minus 0.8, which will give you the delta lambda, divided by 0.8, which is the wavelength on Earth, equals to V divided by 3 times 10 power 8. This will also give you 1.3 times 10 to the power of 7 meter per second. You can use the line that produces electron transition alpha or beta to get the speed, which will give you the same value. Then part C. The galaxy in B is known to be at a distance 5.7 times 10 power 24 meter from the Earth. Use your answer to B part 2, B part 3 to determine a value for the Hubble constant. To do this question which carry 2 marks, you need to know Hubble's law is V equals to HOD. V is the velocity of recession, and D is the distance of the galaxy from Earth. So HO equals to V divided by D, which will give you 1.3 times 10 to the power of 7 from here. Because we know the speed is 1.3 times 10 power 7 meter per second. And then the distance is 5.7 times 10 power 24. This will give you a Hubble value of 2.3 times 10 power minus 18. And then the units is per second. You can see why the unit is per second from here. This is a summary of the facts that you need to know to solve this question. Number 1, you must understand how the line emission spectrum is produced. Number 2, you must recall and use E2 minus E1, which will give a positive value equals to HF. And then number 3, understand that line emission spectrum provides evidence for the existence of discrete energy levels in an isolated atom. Number 4, understand that redshift means that the lines in the emission spectrum from a distant object shows an increase in wavelength from the known values. And then number 5, use delta lambda over lambda approximately equals to delta frequency over frequency approximately equals to V over C to calculate the speed V of a distant galaxy moving away from the observer on Earth. And finally, we can use Hubble's law, which is V equals to HOD, to calculate the Hubble constant.